All right, welcome everybody to the June 2026 MAS monthly meeting. I'm Walt Strabergs, president of the Minnesota Astronomical Society. Uh, and I'll dive right into the agenda for today. So Noha is not here, so I will deliver the treasurer's report unless Noha happens to be online and wants to do it. But then I'll do membership update, Astro events this month. There's a couple cool things going on. Outreach requests and some volunteer opportunities, upcoming MAS events. And then Mark will step up here and do a site update because we ask all of the site leaders to do a presentation sometime during the year. So he's going to talk about the Cedar Creek site and also about the New Mexico Remote Observatory opportunity that we're building. And then Jerry is here, and he's going to have some awards, AL awards. So yay, real Jerry, not virtual Jerry. And then more volunteer opportunities, some PSAs, and then our featured speaker from University of Minnesota, Dr. Ali Sulaiman, is here, and he's going to present in person. All right, so let's go. So starting as usual, 2026 MAS board, I'm Baltz again. John Zimich, our vice president, is here. Raise your hand. Claire is here. Raise your hand. Noha is not here, so she can't raise her hand. Jesse's here and Phil is here as well, board members at large. So if there's any concern, any question on any of the board, any of the MAS operations, please reach out to any of the board members. You can use the form on mnastro.org about board contacts, and you can contact any of us or all of us. New members. We had a whole bunch of new members. And so as of today, or as of a couple days ago, June 4th, we had 705 members. That's not as of May 4th. It was the report early June. So 3 honorary, 149 patron, 527 regular, 26 student. So are there any new members either online or in the room here? Raise your hand. All right. You want to say hi? Welcome. All right. Yeah. Well, we seem to bump up and down over 700 all the time. All right. Astronomical events for June 2026. Always have fun researching all this stuff. June 8th is third quarter moon. June 9th, conjunction of Venus and Jupiter. It's supposed to be pretty nice. Nice. Yep. June 10th, conjunction of Moon and Saturn. Also, June 10th is the daytime Arieted meteor shower. I don't know how much we're going to see of that. June 10th, Mercury is at highest altitude in the evening sky, 16 degrees, so not too bad. June 12th, conjunction of Moon and Mars. June 13th, close approach of Moon and M45. June 14th, new moon, best time. June 15th, asteroid Irene is at opposition, so always have one of those up here. So Mag 93, you can do it. Yeah. Conjunction of Moon and Mercury on the 16th. Close approach of Moon and Jupiter on the 17th. June 17th, also lunar occultation of Venus, and I'll talk a little bit more about that on the next slide. So June 19th, close approach of Venus and M44. June 21st is a solstice, so it's the shortest night, so just get some sleep. Yeah. June 21st, first quarter moon. June 27th, the Boötid meteor shower, and June 29th is that dreaded full moon. Couple comments out there that are astrophotography targets, nothing spectacular at this point. So C2025 R3 Pan-STARRS is still there, but it's fading very fast. Comet 10P Tempel 2 is visible in the sky through August, and Comet 29P Swashman Watchman 1 is out there as well. Yep, it's dim. Yeah, okay. Swashman. All right. Upcoming space events and launches. Some events over the last couple weeks. I don't think we're going to be hearing from Blue Origin anytime soon. Boom, big boom. Yeah. Rocket Factory Augsburg is going to have their maiden, or is scheduling their maiden flight out of Scotland. So that's kind of exciting. New rocket company out of Europe. Themis TH1 is an Ariane suborbital rocket launch. ISAR Spectrum test flight. That's also another European, or is being flying out of Norway. Hopefully they make it this time. Long March 10B and 12B in China have some demo flights, and those are critical to the Chinese lunar program. Interestingly, Pegasus XL, so the Pegasus air launch rocket, we thought was kind of a long dead thing, but they're actually going to try to launch one out of Kwajalein in the Pacific. And it's an interesting mission. It's called the Link mission to service the Swift satellite that is rapidly deorbiting. So it's a test mission to try to boost that early warning satellite up to a higher orbit. So that's kind of it's kind of a cool mission. So there's another mission, Sunrise. It's a 6 CubeSat radio interferometer mission. So that's kind of exciting. And then Tianwen 2, which is a Chinese asteroid mission to Kamo Oaawea. So that will be arriving also in June. So that's exciting to see up close and personal another asteroid. No, not going to do it. So again, most of my sources are from inthesky.org, and basically just scouring the internet and watching for that kind of stuff. So keep your eye out. So the one thing I did want to discuss is on June 17th, the occultation of Venus. So that will be a daytime occultation of Venus of the moon. And actually, we are smack in the middle of the path of this one. So the disappearance is at 1414 CDT, and then reappearance is at 1538. And the position will be, it's going from the dark side, the unlit side of the moon, over the crescent, almost straight through the moon. So it's a pretty long occultation since we're right in the middle of the path. So that's a interesting target. Midday 2 p.m. to 3:30 p.m. target. So get out there in the middle of the day and do that. At least we can do this, close to the summer solstice, so midday. But of course, it might be cloudy, so who knows? But yeah, this is an accurate representation. So it's going to be pretty dim. You're gonna have to find it first. All right, outreach. Lots of outreach opportunities going on. So I'll try to go through from top to bottom. June 24, Dakota Scott County, there's a summer solstice event, and they're looking for a speaker on July 14th through 16th at ELO Baylor Adventure Camp. That's a daytime thing. Looking for help there. August 5th, Minnetonka Community Center. They're requesting a presentation. August 12th, Able Park, Spring Lake Park, not St. Louis Park. Dave Faulkner is coordinating that. So if you are able to help, want to help, go see Dave. August 12th, Osceola, Wisconsin, Standing Cedars Community Land Conservancy has an outreach request. August 13th, City of Delano, 150 years celebration, requesting a speaker. August 22nd, Forestville Mystery Cave State Park Dark Sky Festival. I know that we participated in that a couple times, and it's a star party and a table event. That goes to, so you can do it twice on August 22nd. Yeah, we're looking for 2 people. I'm jet lagged. I just got back from Asia, so I'm terrible. ELO, September 18th, there's a tentative alumni club event. Is that still a thing? Yep. Okay. September 18th, 19th at LLCC, we've got a request. This has to do with the statewide star party organized by the Bell, but the LLCC's portion, they're calling it S'mores and Stars. And so we're short on volunteers up at LLCC. So if you want to help help out that event that weekend, we'd appreciate it. That's one of their public events at LLCC where they're trying to raise some money and trying to get more astronomy outreach to the public up at LLCC. So if you're available at LLCC, make it up there. Probably. They probably would. Yeah. So look online on the forum, and David is coordinating that, so he's going to be able to tell you whether we've got accommodations. But I think we do. David Schaff. Yep. All right. Then October 26th, either at JJC or somewhere else, Bayport Cub Scout Pack is looking for some an event for their scouts. And then November 5th, it's a flexible date at the Victoria Library. They're looking for an astronomy presentation. So as usual, I think I got most of them, but there might be a couple that I'm missing still. So look at the MAS forum, look at the MAS outreach Slack channel for the latest and greatest. Contact our great outreach committee, and one of the outreach committee people will reach out to you and find out what's going on, and we can go from there. All right. Thank you all. Thank you to all the outreach volunteers that we get. Okay, beginner special interest group observing session, Saturday, June 6th, 8 p.m. at Metcalf. Okay, there's a sign up on the website or sign up on the forum. Suresh will coordinate that and let people know whether it's a go or no go, but it looks like it's a go, so it's a go. So Saturday at 8 p.m., 9 in a row. So BSIGs are doing good. Yep. So if you subscribe to the calendar, it should automatically be on your phone or on your email. You can get that all the time. But be sure to let Suresh know that you're coming so he can keep track of everybody who's coming and going. All right, BSIG. Other upcoming MAS events. So June 6th, also ELO, there's a public star party. Tanya Melnick will be speaking, I assume about auroras. June 6th, BSIG, like I just mentioned. June 12th through 13th is LCC member observing weekend. So sign up on the forum. Make sure you reserve a spot if you want to go up there. June 12th, that's a Friday, CGO member star party down at Cherry Grove. May 9th is another ELO public star party. I'm not sure if there's a speaker scheduled at this point. Not May. I don't know. May 9th, May 9th. I don't know. It's all the same. I need to do a better job at these. No, it's not. I did, actually. It's a long flight from Manila. Yeah. So anyway, June 19th, 21st, LLCC member observing weekend. And then July 2nd, right here, MAS monthly meeting. And we're going to have a bunch of member presentations. We're not going to have one single speaker. We're going to have a series of member presentations. So key holder trainings. The upcoming key holder trainings are a little scheduled out. So ELO, the next one scheduled is August 1st. ELO JJC keyholder training scheduled July 25th, and sign up on the forum. The ELO keyholder training, there's a website form you can fill out to sign up. And then Cherry Grove, there's a forum sign up as well, and the training is July 10th. And then LLCC training is during Northern Night Starfest in September, or by special request. If you go up there and there's other key holders up there, we can show you around. So those are upcoming key holder events and key holder training sessions. All right, Mr. Ahmed has something to say.
Okay, it's time of the year where I start asking for astrophotography pictures. So as usual, for the past 6+ years now, we've done members astrophotography, and this is going to be our 7th one. That's going to be for the August meeting. So pretty much, if you've gone through this, you know the procedure. But if not, it's pretty much, there's the email programs at mnastro.org. send me 2 pictures or 1 time lapse. Give me your best. And, a brief inside email to the email, and make sure you send it to me by July 31st, 11 p.m. or midnight, just end of July 31st. That gives me a couple days to consolidate stuff and put together the slide deck before the meeting. And if I know some people, they don't know which one is best. If you send me a couple, then you leave it up to me to decide if you send me more than 2, you leave it up to me to decide which ones are better or best. So if you don't want me to do that, just make sure you only send me 2. Now, as usual, also, we're also going to be doing door prizes. It's not a competition between pictures. It's just that in the end, if you've submitted a picture, you came and spoke to it, for those in the room, or even online, we're just going to be doing a quick, the spin the wheel like we've done it the past couple of years. We're still thinking about prizes. Last year, we had books from Andy Weir. The year before, we had books from Dave Faulkner. This year, we're trying to think of something else. So we'll come up with something and it will be fun, like every year. Questions? Go ahead, Dave.
For the movie, what's the maximum length of time you're going to
No,
No,
no.
I would say 2 minutes max.
Yeah, 2 to 3 minutes is reasonable.
Yeah.
For a time lapse. Please don't send me a 10-minute. Now, I know some of you put music into your time lapse. If you're doing that, please indicate that in the email so I can try to figure out a way to get it to run with the music. But if you don't tell me, I'm going to incorporate it. I'm not going to watch the whole thing. I'm not going to know what it has. So we might be missing that detail.
And if you do have music in your background and pictures, make sure it's we'll get copyright striked if
Oh, yes.
on YouTube if we publish it. It'll just get erased out of YouTube. So it's better either to not put music or put copyright free, free open source music. There you go.
Any other questions? Okay, send me your good pictures, and if you don't know which one, send me more, but I'll be picking.
Yeah.
Thank you.
All right. Thanks, Ahmed. All right. The big events are still upcoming for MAS. So Northern Nights Starfest, I mentioned before, September 9 through 14th. You can register by going to the calendar link at mnastro.org event 2026-NNSF, or just look on the calendar. And there will be a registration link to Camp Brain registration. The registration is managed by LLCC. So, and we are still looking for a couple speakers. We've got a bunch of speakers already lined up, including Bob King and a bunch of others. So, if you want to speak at NNSF, just let me know and we'll get you on the schedule. And we're looking forward to seeing you in September. And then Camping with the Stars is at ELO August 14th through the 16th. And that's registration. You can get to the registration page also through the MAS calendar, the event 2026 Camping with the Stars. On that page, there's a link to the Carver County site that actually lets you do the camping and the day pass registration. So that's available, and I know that the ELO committee is working hard to put together speakers and activities and food for people. And it's usually a fun time. It's a fun weekend. So that's the other thing going on, the other big event. All right. All right, Mark, you're up. Or you can use the clicker.
Cool.
You're there.
All right. Good evening, everybody. I'm Mark Job. I am, I guess I'm the nominated leader for Cedar Creek. Spokesperson, maybe that's it. So Cedar Creek, long name, Cedar Creek Ecosystem Science Reserve. We've had this great relationship with them. What is it? Going on 7, 8, 9. It's been a while. I mean, it's been a while, and it's a really awesome relationship. It's kind of interesting. I was on the website and I go, wow, that's the picture they have. That's the old, well, you can't call it the old facility. That's the old configuration. Everything is still there, but then they added this wing out on the east side, which essentially doubled their classroom space and added facilities and things like that. So the whole story behind that is they use this place during the day when it's sunny, and then they turn it over to us whenever we want, because we can decide when we're going to have a program there. We can decide basically any time of nighttime activities. It's also open for the volunteers that put in time up there. They also can arrange for private star parties. I've had in the back of my mind to have an astrophotography thing up there, but every time I put that in my mind, well, then it pretty much guarantees that it's going to be cloudy. So I don't think about that anymore. But so the building that you saw here, they refer to that as the Lindemann. That's the old Lindemann building. And for the life of me, I can't find on their website what the name of the addition is. But the addition is really cool, and we can use that. We just haven't yet, because we would set up way on the east side, and if there was something good in the east, and if we had a really clear night with a nice horizon, we probably would go over there. But it's been just how it's been this spring, cloudy, easy. We've had some good nights up there, but that new facility would be great. I mean, we'd have our own door, everybody'd be right there. There's a classroom there. And the beauty of it is as long as we turn off the lights and turn on the lights, because we have the ability to go in the fuse boxes and turn off lights and make that place pretty dark. I mean, it's so dark up there that I can say that I've been up there on a moonless night, around midnight, and I've seen the Milky Way up there. So now the Milky Way is, you can't really capture it until you get above the city lights and the suburban lights that are there. But straight up, it's there, probably from 45 to 45, 45 across east to west. So I would say it's probably as dark as ELO. It's kind of a pocket there. It's kind of cool. If you look even at the dark sky maps, you'll see that there's a little pocket of dark, and that's Cedar Creek. They do a good job for the most part on their property about keeping lights away. I've talked to them about their parking lot lights and the lights that they think that have to be on all night. It's a power struggle between them and the university, because it is property of the University of Minnesota. So that's the struggle, is that for whatever reason, those lights have to be on. So we let them be on until we get there, and then we go find the circuit breaker and we turn them off. And it's been a lot of fun. I mean, I would say this spring we've had 3 star parties, and I think we probably average 25 to 30 people a night. Sometimes the 25 counts the 12 people that are MAS members, but that doesn't count because we're counting bodies. And that's what we report to them. Let's see, anything else I want to talk about? So they also, so we're a guest and they invite us there, and we just need to respect the place. That place is research for somebody. Some students and faculty are using that as research for their papers and things like that. So and we're fine with that, because we just want space around the building. We want to get inside and use their biffy. That's important things for us. We want to be able to turn off lights. So we have no problem respecting their space. And we understand that. And, like I say, we've got such a good relationship with them. They give us the keys to the kingdom, and, they don't even show up. We get in there and we can do whatever we need to do. Yeah, let's move on. So there's schools. So during the school year, September to now, because I even think last week when I was communicating with Kara, they still had schools showing up for so they have day school outside. As you can see in that photo, they're right out there in the water. I believe that is Cedar Bog. That might be Cedar Bog Lake, as a matter of fact. So the classroom becomes the outside, and they teach all kinds of stuff. So kindergarten through 12. Hands-on stuff. And then they have public programs. So we, as the public, can show up there. If you go on their website, they have programs all the time where they have things going on. They'll do hikes in the woods and out to their bog, because they have a bog. It's pretty cool. I've been out there, and it's very interesting. So it gives them an opportunity for them to give back to the community that they are in, and then they invite the community in. So it's pretty cool. So we have these events left for the rest of the year. August is August, but we have 2 events in August, just because we're trying to capture and trying to engage the community that they're in, the people that are around there, to let them know that we're going to be there. And since school's not in, come on out, we'll show you the stars. And one of those on purpose was almost a moonless night. So, oh no, it's not moonless. I'm sorry. There is moon both nights. And then in September, we're doing that didn't get on there. We're doing a solar event. So in the afternoon, starting at 1 until I think 3 or 4, we'll have solar scopes there, and numerous MAS members with their solar telescopes, and we'll show off the sun. And Cedar Creek is staffed. They'll actually have some little activities for kids inside where it's cool and things like that. And then obviously we have the sun, and they're very inviting for us, because they set up a tent for us. They make sure that we have shade. They make sure we have water, and sometimes they even feed us. So that hasn't been talked about yet. And then we have the last 2 events. It's pretty cool. Questions? No.
That's Bellwin.
No, they have one too.
Oh, they did?
Yeah, because they have Oak Savannas there too. And for the same reason that Bellwin does, they bring in the buffalo. They just haven't in a while. That I remember seeing that somebody was asking the last summer, when some people showed up for a star party, they asked somebody, hey, they got the buffalo. No, the buffalo aren't here again this year. So it's been a while, but I know it's part of their program. It's something they want to do, because, for the same reason Bellwin does, they want those buffalo to be out trampling around underneath those oak trees, doing what they do. Fertilized. So next slide here is, so the Minnesota Astronomical Society is going remote. So a group of us have been tasked with figuring out a space, figuring out equipment, figure out how we can do this within the club. So we've kind of got a backbone set up where we have equipment. We're going to use MAS donated equipment as much as we can, and where we can't, we have a budget that's supported by some very generous donations. So it really won't be any pressure on the MAS budget, so to speak. We're working out a really good deal where it won't really cost us anything for the space that we're going to get. So that will be given to us, and it's by a generous MAS member that's going to give us a pier in his building in New Mexico. And if you think of New Mexico, where the little tab sticks down toward Mexico, that's where we're going to be. We're going to be just above that little tab, closest to Arizona, actually, we could say. I think if you whip the stone really hard, I think you could still get the stone into Arizona, I'm pretty sure, because it's pretty close. And, we've been talking about, is there going to be a problem with security? Is there going to be a problem with, people coming, taking our stuff? But it sounds like there's a lot of patrol there, because that is also seems like it used to be a highway of trafficking come through there, and it sounds like they pretty much squashed it down. And from what I've heard, there's very little. Plus, there's some other bigger outfits, bigger than us, that are going to be there. So small investment, small risk for the club, and we're almost there. We have equipment. We're going into this space. We get one of those piers, not sure which yet, but We don't know too much about the other two. Other than I think the owner is going to take another one. But he also said that if he gets enough interest, he's got enough land, he'd build another building. What's the name of that place in Texas where we went, Chris?
Starfront.
Starfront. Yeah, it's going to be Starfront West, but he'll have to. He's got a couple to go. Yeah. So anyway, whoops, did I go the wrong way? Huh, interesting. So there's our equipment. It's currently residing in my observatory in Buffalo. Only the RC optics scope, that other refractor there, that's mine. We decided we weren't going to take it off because it would kind of help with the balance anyway. And since we took my plane wave off to replace it, it wasn't too big of a deal to get it rebalanced. So we left it on. But as you can see in the picture is, it's that big scope. It was donated to the club. It came with, it had a focuser and it had a rotator and it had a bunch of other stuff. Some of the stuff we couldn't use, but we are going to use the rotator. Vaults tore that thing apart, I think, and got her all lubed up and cleaned up, and it actually works pretty good. The focuser, we're on second revision of the refurbishment because the first one, the steps were, we had a 5-to-1 gear reduction in there. We had to go to 101 because we didn't have enough steps. I think that's the highest we can go. Can we go one more?
We can go 250 to 1.
Oh, 250 to 1? Yeah. Well, I don't think we want to go there. I think it seems to be working at 100 to 1. So now if we can get the filter wheel fixed, because that was the latest and greatest little problem we had. I think it was kind of one of those deals is we got it all installed and the things we were worried about is focus and rotate and how good's, how good's the image? Do we have to collimate? Do we have to tear the whole thing apart again? And we never worried about I'll take full responsibility. I never checked to make sure that the filter wheel was being recognized as a 7-position filter wheel. Because I didn't care. We were only looking at luminance. And then one night just recently, we went, hey, let's test this thing and try more than one filter. And when we came around to do flats the next day, went, why do I have to take a 5-minute flat on a broadband filter? There's something up. So I know that's okay, but that's okay. There's a good population of imaging people in here that understand that. So the software was recognizing the fact that we only had eventually it was just a 3-position filter wheel when we truly had a 7. I worked with the guy from China at QHY, and he did all the things that I've done and that everybody else has done that we're helping out. And he says, I think there's something wrong with the communication between the camera and the filter wheel because they're connected together. So the scope is in excellent shape. This model of the Ricos was built in 2006. I believe we were the 3rd owner.
Yes.
And like I say, it's in excellent shape. I mean, we haven't touched the collimation at all, and it's bounced all over the place. It's been to CGO, it's been to the storage shed, it's been wherever it came from, New Mexico. So it's a 2850, I believe, is the focal length. It's an f9. It's 12.5 inches in diameter. We have a QHY 600 monochrome camera on there. And like I said before, a 7-position filter wheel with 2-inch filters, LRGB, hydrogen, sulfur, and oxygen. Yes. 3 nanometer Optolong. We went where we could get the best deal for the best filter. So anything I miss? Let's see. So I think we're getting close. I mean, had we not had this filter wheel issue, I think we would be in full swing testing and we'd be looking for people to test. I think that's where we are. you don't have to come. Stay at your house. Because Conrad Sanders one night ran this thing from about 10 o'clock, 9 o'clock, because I think it was still getting dark by 9 o'clock then, until about midnight. And Conrad, I don't remember, is it 20 minutes, 30 minutes, 30 minutes? Is it six block? Yeah, but how many R's and how many G's and how many B's? That doesn't sound right. Because that's hours. Over 3 hours. So anyway, I think this picture is about 2 hours of stuff over 3 filters. So it probably was about 40 minutes. So 5-minute subs. This is 5-minute subs. We were using the guider. Oh my goodness, I can't believe I just said that. We're using a guider. But I know that scope, I was doing it before the scope was even set up when we were checking collimation. I was doing 5-minute subs without guiding and they were fine. They looked as good as this. So yeah, right. So this is M81. And M81 is nice and high. You know, basically that night it probably was at the zenith, because that's where it is these days. So it's gone well. I mean, we've done a good job testing, and I just need. And when we get the filter wheel back and we get it back installed, I'm just gonna need somebody else to do it because, frankly, I'm kind of getting tired of that thing because it kind of irritates me some nights. F9, no reducer. We thought
There's a
there was.
flattener, but no reducer.
Yeah, it's flat but not reduced. No. Always an F9. Yes, it's gonna be awesome. Awesome.
And south, much farther
Yeah,
south.
yeah. You're gonna be at 32 degrees, something like that. You know.
Yeah, it's Bortle 1. It's border.
Yeah, it's Bortle. It's a Bortle 1 sky. You know, I can't. I mean, the closest town that you fly into would be Tucson. You know, I mean, and I think that's like 2.5 hours away. I believe that's what we've been told. So, hi, Russ. Any questions, Conrad? Yeah, right. Yeah. Yeah, so what Conrad is talking about is he's cropped this image quite a bit because we were having some trouble. Obviously, it was related to the filter wheel problem. And I mean, that's going to go away as soon as we get that filter wheel fixed and get it back and get it installed, and we'll do some more testing. QHY has been just absolutely outstanding and totally listening. They logged into the computer and they took over and they troubleshot this, and that's why we are where we are. And the filter wheel actually is in transit to the service center, I believe in New Jersey, and it'll be delivered on Monday, and they'll troubleshoot and they'll figure out what's up, and then we'll be on our way. Any other questions? John? Well, that was a little while ago. I had a slide for questions then.
Okay, the question I had was, I don't remember the dates of the solar observing because there's a solar eclipse on the 12th, and I'm not sure if it's going to be partial here in the afternoon. I don't know if that was one of your dates.
I don't think it's here. I think it's just a little nibble. I don't even think it's close. I would say, I think our solar date is in September. And it might be like the 18th, 19th, something like that. It's when put it this way, there's non-eclipse that night because that's also star party night. And I know we're going to see the moon. There you go. September 19th. So is it 2 o'clock to 4 o'clock? Something like that. Yeah. So, oh, well, I'll be there. Anybody else? Any questions? Oh, there's my any questions.
All right. Thanks, Mark.
I'm done now.
Yeah, so on the New Mexico scope, the best case scenario is that we haul the equipment down this fall and set it up over the winter, have it available for early next year. So that would be the ideal situation, but all that still has to be worked out. But lots of progress so far. Oh yeah, and the Paramount that the mount that's going on is also a donated piece of equipment. So all of the equipment except for the camera was donated. Chuck, yeah. Oh yeah, absolutely. Yeah, all that has to get worked out. There's going to be the connectivity, we have to work out the file transfer, all that stuff. So there's still a lot of work to do, but the meat of the hardware stuff is past us, I think. And so I think we are just waiting to get that thing deployed, get the hardware back and ready to go. Absolutely. And the software, we are running Nina, so most everybody's familiar with Nina. So it'll be anyone astrophotographers familiar with that software will be able to run this. So yep. All right, Astronomical League awards, Mr. Jerry Jones.
Good
Welcome,
evening,
Jeremy.
everyone. I have one award for this evening. Tom Holman. Applause, 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 applause. Applause, applause. Amaze, amaze, amaze. Applause, 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 applause. The Holton ARP Award, which is challenging. Congratulations. Would you share us a little bit about what this award is and how you did it?
Right, I got.
Oh, he's ready. Impressive.
So you have to take 100 images or 100 observations of these ARP peculiar galaxies, which are irregular galaxies. There's like 360 of them in the catalog. I did them all around the same time of year because they were all about the same place in the atmosphere. A couple of them are difficult. I got a couple of them that are 200, 300 million light years away, which are fun. Some are really interesting looking, like I guess you guys have probably seen the penguin and egg galaxy and the antenna galaxy, those kind of cool ones, the two in a view kind of thing. But then some of the Messier objects are also in the list, like M90, M51, M60. So there's irregularly shaped spiral galaxies, irregularly shaped elliptical galaxies. There's galaxies that lack a clear shape, and then there are pairs, and then there are 7 other, and that's that.
And what equipment did you use?
Oh, I used the C-Star S50. So, yeah, that's right. So this is this is my 9th deep space challenge, and I also have a solar eclipse, so it makes 10. And I'm getting close to getting the last one I need, which is the asteroid tracking one, NEO.
Congratulations. So I want to bend your ear for just a second more. Any of you were surprised at the amount of money that we send to Astronomical League? No? You wouldn't be, obviously. One of the values that we gain from being members of the Astronomical League are all these observing opportunities, observing and imaging opportunities. And one that I want to highlight very briefly for the summer, because this is the best time to do it, is the globular cluster list. The summertime is where the globs are, most of them are most visible. And it's really a magnificent list. Even if you're not interested in completing the project and to get the bling, what it is, it's a curated list of the best globs available to us. And you can download the list and you can use it as a what should I look at tonight? As opposed to, well, I'm going to look at the same stuff I've already done, the ring and, what else is out there that I can see, and the summertime is best for globs. So I would encourage you to take a look at the AL list for globular clusters, if for no other reason, just to have the list there and say, what else can I look at tonight? Look at that. There's a bunch of globs. Ophiuchus, there's a bunch of globs in there. And I think you will find that a valuable thing to do as you're observing. And everyone is pointing to the dear woman behind because she was the one who did. And Claire said she did it over the summer and it was the most amazing thing and she loved it. She had a blast. It is a great list, especially if you figure out how to do the Shapley-Sawyer designations fairly quickly. That was great. That was Trumpler. Trumpler's tough. But that's open. That's open clusters. I'm not encouraging it necessarily today. Today it's globs. It's globs, which is great. All right. Thanks very much, folks.
Thank you very much, Jerry. While we're still on the Astronomical League, a couple notes. Alcon 2026 is being hosted in Cincinnati, August 12th through the 15th. So if you're interested in that kind of thing, you can visit their website, alcon2026.org. And then, as usual, I still highlight the AL Special Observing Challenges that they list on their website. So number 10 is still out there, T Corona Borealis. Still hasn't blown. It's going to blow someday. It's going to blow someday. So we'll go. Yeah, let's see if that one comes through. June 25th. Yeah, I really trust Forbes for my astronomical predictions. Yeah, and then the observing challenge number 16 is M102, Messier's Unknown Journey Observing Challenge, and that deadline for submission is July 31st. So look on the AL website for all of that stuff. So as Jerry usually say, let's see if this thing works this time. Well, let's do it.
And observe or image.
Yay.
Get out there and observe or image. Get out there and observe or image.
No. Okay, volunteer opportunities. Always. Again, we have an official grant committee. It's not official, but it's basically NOHA. But she's looking for help. So when we have projects of a bigger nature where we want to build something or do something or do something especially for the public, we have opportunities to write grants. So there's a little bit of work involved to write the paperwork and submit the paperwork. So that's one way. Other ways, presentations. So next month we're going to have a bunch of member presentations instead of one main speaker. And so always member presentations. I try to have one member presentation or student presentation every month, but we don't have one this month, but we got plenty of speakers. So write articles for Gemini. So Father Brown has always been hounding us for articles on Gemini, and I think that's just going to keep going and going and going. Web team also always needs a little bit of help. So if people have WordPress experience, PHP, BB Forum, some technical stuff, some behind the scenes stuff, we're looking for help there as well. Join a committee. Most of our committees are fully staffed at this point, but there's always turnover committees. People move on, people step down. And sometimes there's other opportunities to do it. If there's a new project that comes up, we'll form a new committee. So help out at a public star party, especially at ELO, Cedar Creek, and at BSIG. So come and do your duty and help the public learn how to use their telescopes, present the MAS observatories in their best light, and let's teach the public and inspire the younger generation. And then, as I already mentioned, outreach. There's a lot of outreach opportunities statewide. From Forestville Mystery Cave down in the south of Minnesota, all over Minnesota, especially in the Twin Cities area, urban, in various parks. Another thing is like Michael Copper hosts the Planets in the Park every so often in the city of Minneapolis. Just a great way to help out. All right. So presentations. So what can you write a presentation about? Pretty much anything. And this goes for writing Gemini articles too. So if whether you have observing campaigns, astronomical objects that are your favorite, like Trumpler open clusters, you want to write about those? History topics, adventures to dark sky sites, astronomical sites around the world. If you're traveling around the world, ATM projects, if you build something cool, restore some old piece of an antique telescope or something. If you have a special outreach project or have an outreach story to tell, that's always a good presentation. Imaging techniques, observing techniques, research topics, whether you're doing variable star observing or you're doing occultation timings or any of that kind of stuff. Scientific related stuff is interesting. How-tos about software, telescopes, new telescopes, new optics, manned or robotic space missions. And even we can whip out the old 3-ring binder and John can do another Better Know a constellation. Or if we want to do that every single month, that's fine too. So it's a great experience. You only need like 10 minutes or so, 10 or 12 slides, 15 slides. Not hard to do, not hard to put together. It's a great experience to get out and speak in front of a crowd. So if you got any ideas, if you want to participate, if you want to be a member presenter, contact Ahmed at programs@mnastro.org. All right, Loner Scope Program. John, you want to talk about loners? Or is Anton here? I don't see Anton, so John can cover it.
Okay, the Loner Scope Program. I know we have one new person in the room. Are you aware of the Loner Scope Program? Oh, so I don't need to say anything. No, well, just to rehash a little bit, Loner Scope Program, we currently have 19 different pieces of equipment that you can check out for 1 month in the club, and we just go out to the website. You can, as the slide shows there, how to get there. You fill in your name, you fill it out, and you get on the list to get one. We're in observing season, so right now the big popular scopes are the SCTs and the 8-inch Dobbs, and but there's other things. There's binoculars, there's smaller telescopes. There we have a solar telescope as well that we just refurbished. And according to Volts, it's beautiful, right?
It is. And soon to come, we're not ready yet, but this is a unistellar EV scope, so that will become part of the loaner program. We'll have a special process for loaning these guys out, but we're going to have this EV scope, and we are going to be getting a C-Star S50 also as a loaner. So we'll have a couple of electronic scopes available. So not available yet today, but this will be coming in the next few months. And if somebody wants to step up and be a coordinator for that program for the loaners, electronic loaners, please come and see me. But I think that's going to be an exciting addition to the loaner scope program.
Yes, and we didn't want to overstress Anton. He's doing a wonderful job with these scopes, and the EV scopes is going to take another bit of time coordinating with people, training, that sort of thing. And so when we step forward, it'd be nice, you just be aware of that. You're not going to have many scopes, but it's going to be using the same process. And we'll just, those requests will come in to who's ever coordinating that. And we also have the great courses available on DVDs, and those are available as well to check out and look at those. Any questions?
All right, thanks, John. All right, weekly happenings. So pretty much every week, if there is a current event happening, our Secretary Claire will put together the weekly happenings newsletter. It's being sent through MailChimp, and basically it goes out every Tuesday when there is information and content to be published. So if you have something to be published in the weekly happenings, please send an email to the secretary, Claire, at secretary@mnastro.org, and she will include it in the next upcoming weekly happenings newsletter. We try to put the upcoming events in the next week, and any other important information, especially when it comes to election time and some of the other budgeting events and all that kind of stuff too. So send posting requests to Claire at this address. You can subscribe. So most members automatically who become members get onto this email list. But anyone can subscribe to the email list by filling out this form on the homepage. Just put in your name and your email. It's all you need. Doesn't cost anything, and you don't have to be a member to get it. Yes. Absolutely, she does. All right. Other online resources that we have, we've got a Slack channel, so members have opportunity to join the Slack community. Slack is a tool for collaboration, file sharing. Most of the astrophotographers now use the Slack astrophotography channel rather than the forum to share images on that. And it's just a good real-time discussion. You can have huddles, you can do video chats. It works on mobile, it works on computers. It's a great tool. It's a great resource, share files and all that kind of stuff. As well, we also have the forum at the PHP-BB forum, which is the traditional bulletin board type forum. We've got most of the MAS operations there, so all the sites have their private committee channels there, their open public channels about information about upcoming star parties. We put other information there. A lot of the interest groups also have channels onto that forums as well. We have a presence on YouTube. This meeting, all of the BSIG wintertime meetings are recorded and edited into YouTube and archived so far forever. We've got probably over a couple hundred different recordings on YouTube at this point. And so you can always go back and search YouTube and look at a presentation that you might have missed. We have a presence on Instagram and on Facebook. So if you want to publish an image or something with the Minnesota Astronomical Society pages, please send your link or your image to social media at mnastro.org, and Chris will post it for you. Make sure you watermark your image. Take credit for the images that you create. All right. Official mass stuff. So last month we announced our new store, Redbubble, and there's been some movement on Redbubble merchandise. But the board decided to, since we started with Cafe Press, we also looked at a company called Spreadshirt. We basically have stores set up in all three of those sites. So if you don't like what's on Redbubble, Cafe Press is still open. We have links to Cafe Press, and we also opened up the link to Spreadshirt. So if you like if you like Spreadshirt better, you like their merchandise, you'll have better colors, they have better swag, then go to Spreadshirt. But all three are available. All three are linked directly from the homepage in the About section, MAS merchandise, and there's links to all three of the official stores. So good stuff. Gemini. So I announced last month that Father Brown has decided to step down as editor. So in the October issue, that will be his last issue. But the board has unanimously elected Roger Cowie as our next Gemini editor. So Roger will be working with Father Brown over the next few months. And hopefully, by this fall, Roger will start putting his special touches on the Gemini, and we'll make Gemini just keep it going and make it even better than it is today. So Roger, welcome. And we look forward to you and Father Brown working together and just keeping Gemini the best publication in amateur astronomy clubs in the US. Thanks. All right. Gemini articles. So I'm sure Roger is going to follow up with Father Brown and hound everybody for more and more articles. Just like I said about presentations, Write about anything. Write about your experiences, equipment, successes, challenges, imaging tips, ideas, anything. Send in photos. The Geminis are all archived on the website in PDF form. You can go back all the way to 1972 and read Gemini articles or read the Twin City Astronomy Club articles from way back then. So if you have new articles and you want to submit article to the next published Gemini, email gemini@mnastro.org, and that will get to Father Brown and to now Roger, and we will start putting together the next issue. So articles. Please submit articles. Okay, we have come now to our featured speaker. So Dr. Ali Sulaiman is a PhD and got his PhD from Imperial College in London. He was the assistant research scientist in the University of Iowa, also got a postdoc in Iowa as well. His research topics are planetary magnetospheres, auroras, ionospheres, giant planet research, solar winds, and plasma physics. So let's welcome Dr. Sulaiman.
Okay, well, thank you for having me. It's great to be back. Today I'll give an overview of the Juno mission, which is the only spacecraft in the outer solar system, and it is currently in orbit around Jupiter. So here we have an image of Jupiter captured by the James Webb Space Telescope, and right there is Juno. I stuck that image right there. The first orbiter around Jupiter was Galileo. So although Juno is the second orbiter, it's the first polar orbiter. So it's giving us unique access to the polar regions and the auroras as well. And what's quite nice is you can see in ultraviolet emission the aurora in both the northern and southern poles, and there's a nice vertical extent to them. Now, in addition, you can see the gossamer rings, very diffuse rings around Jupiter. This is Adrastea, this is Amalthea, and this diffuse emission here is actually coming from Io, the innermost Galilean moon of Jupiter, which I'll talk a little bit about in this presentation. Oh, and I should say, if you have any questions, please feel free to ask in real time. You don't have to wait until the end, especially since I might be jumping from one area to another. Okay, so when it comes to exploration of the outer solar system, at least through the eyes of spacecraft, it all started with the Voyager mission. So there are two spacecraft launched about 2 weeks apart or so in the late 70s. And it was a very opportune time for that because the outer planets were perfectly aligned such that these spacecraft were able to execute the so-called Grand Tour. Voyager 2 flew past all the outer planets, Jupiter, Saturn, Uranus, Neptune. Voyager 1 took a detour. When it flew past Saturn, it found Titan to be quite exciting. It had a haze to it, a very thick atmosphere, and so the change in orbit took it out of the ecliptic plane. So today they are interstellar spacecraft, and they give us multi-point measurement, sort of three-dimensional view, if you like, of our heliospheric bubble and the interstellar medium as well. So Voyager officially left the solar system, again, depending on how you define what the edge of the solar system is, but the way it was defined from Voyager measurements, that exit took place in 2013. And actually, it was the discovery was made by the instrument built at the University of Iowa. That was the plasma wave instrument. And here, the definition of the edge of the solar system is the heliopause. Okay, so if you like, that's the last magnetic field line that's connected to the sun. So inward of that, you're in the heliosphere, you're in this bubble that is dominated by the solar wind, that is plasma emanating from the sun, and you're connected to the sun's magnetic field. And beyond that, you're in interstellar space. So you're connected to some other star's magnetic field or the galactic magnetic field as well. Okay, Inside the Voyager spacecraft, we have the famous golden disk that has messages from humanity. So you have the anatomy of man and woman. You have also the golden disc with a record player and instructions on how to use it. You have the sounds of the breeze and leaves and animals such as dolphins, and you have the human voice as well. And there's also a map of where we're located in the solar system, the third planet from the sun. Whether that's a good idea or not, we'll find out. And then there's also a note from President Jimmy Carter at the time that reads, this is a quote from a longer speech. "This record represents our hope and our determination and our goodwill in a vast and awesome universe. We are attempting to survive our time so we may live into yours." And on its way out, so this is Voyager 1, it went out of the ecliptic plane, it turned around and it took a family portrait of our solar system. And you can see each of the planet here except Mercury. This is the famous pale blue dot that Carl Sagan had a famous quote about. And you can see the Earth was caught in a sunbeam. I was actually at a talk 2 weeks ago about how the pale blue dot was discovered, and it was really, really interesting. A lot of work went into finding that pixel in the image that was taken. And actually, a lot of serious planning went into this family portrait imaging of Voyager 1. It was a very non-trivial exercise. So to give a sense, okay, let's see. Okay, just to make sure I've got. Okay, there we go. Okay, so to give you a 3D view of our heliosphere, so you can see this bubble is the region in space that is dominated by the sun's plasma. The sun is blowing off the solar wind. So there's that continuous stream of charged particles emanating from the sun. And it goes all the way to the edge of the heliosphere and it turns around. And that deflection is caused by the boundary that is the heliopause, again, which represents the last magnetic field line that is connected to the sun. This is actually an old image because it was thought that there would be a bow shock upstream. Essentially, our solar system is sweeping through the Milky Way. So in the rest frame of our solar system, you have the interstellar wind that's blowing past it. And that interstellar wind is dragging along its own magnetic field, and they can't mix with the sun's magnetic field because of Maxwell's equations. So that's why the sun's magnetic field acts as a boundary. And it was thought that that was supersonic, and so you would see a bow shock. So just like you'd see a shock wave upstream of a fighter jet, for example. But actually the evidence now shows that the flow is subsonic, so there is no bow shock. But again, you still get that deflection, and the shape is believed to be as such. Again, by having Voyager 1 go out of the ecliptic and Voyager 2 along the ecliptic, you can get a three-dimensional sense of what the structure looks like. And that's 50 astronomical units to give you a sense of the scale. Now, if we go farther out, this is a logarithmic scale in astronomical unit. So starting from the sun, you have Earth at 1 AU, and then you have Jupiter at 5 AU, which will be the focus of the talk today. So we're still very close to home, even though it took a very long time for Juno to get to Jupiter and for Cassini to get to Saturn, which I'll talk a little bit about later, and a little bit about the first orbiter to Uranus. But again, our solar system encompasses, of course, all of our planets, and then about 100 AU, we have Voyager 1 sitting there. In terms of light time, it's approximately a light day away. So it takes 2 days to hear back from Voyager 2, 1 day for the command to Voyager 1, 1 day for the command to go up to it, and another day for it to talk back at us. And it's still going, by the way, although there are some serious signs of decline. And then you get from about 10,000 to 100,000, you get the Oort cloud. And then our closest neighbor, Alpha Centauri, sits right there, about 4 light years or so away. Okay. Okay, so before I go into the science and give a sense of the highlights of the Juno mission, I thought it's important to address this question, which is whether space is empty. You know, we sometimes talk about the vacuum of space. If you scream in space, no one will be there to hear you. It's all true, but not entirely true. Well, no one will hear you. That is true. So air contains, I haven't counted these zeros in a while, but it contains that many particles per cubic centimeter. And again, of course, we think of air as this very tenuous medium with largely empty space, which is true. But regardless of that, if you consider a volume of a sugar cube, it has that many particles within it. Now, space contains 1 particle per cubic centimeter. And that is enough to be the difference between nothing and something really significant. Okay, so what is that something? So if we look at the states of matter, like we learned at school, we know that we start as a solid. The coldest objects will be in the solid state, where the molecules or the atoms are very closely packed. And if we heat up the solid, it will turn into a liquid. So the molecules still have some attraction between one another, but they can slide past each other. So although it doesn't maintain its shape, it still occupies a fixed volume. And then if you heat a liquid further, you get to gas. So the intermolecular bonds become weaker, and then these molecules can really freely flow past one another and actually can go far enough so as not to be bound or make contact with the particle that it started with. Now, you can heat up gases further, and when you do that, you get to the 4th state of matter, which is a plasma. So we'll go back here. Then. So what happens is now, when we were going from solid liquid to gas, we were thinking about the interatomic bonds. Okay, so at some point you can break them, and then you just have 2 particles that are independently moving as they do in a gas. But if you heat it further, then the intraatomic bonds, so that is the electrostatic force between the nucleus, which is positively charged, and the electrons, which are orbiting, those break up, and essentially you have an ionized gas. And so no electron is now tied to a nucleus. Okay, so everything is flowing past one another. But on the whole, this is still a neutral gas because you still have the same number of positively charged nuclei and negatively charged electrons. Okay, so the main difference is that it's electrically conducting. It responds to electric fields, but also more importantly, because we're thinking about space and the sun and planets, this gas now interacts with magnetic fields. And that's very important because this enables a collective behavior, and I'll come into that in a moment. Okay, so any questions? I realize I opened it to questions, but I'm spending my time looking at the screen, so just to make sure I haven't missed any hand, and feel free to wave to catch my attention. Okay, so although plasma is somewhat of an exotic phase of matter, it rarely occurs naturally on Earth. We do see it every now and again, like lightning, for example, is an example of plasma. It makes up 99.9% of the visible universe. Okay, so here's an entire universe of plasma right here. So all the stars, the galaxy, even the dust that are ionized, you can have dusty plasmas. So pretty much all the objects that you observe in your telescope and everything in between, other than the planets, which make up a very tiny fraction of visible matter, those are pretty much plasma. So you have the galaxies and you have the filaments. Everything is a plasma in the visible universe. And what I mean by visible, I mean I'm not counting, say, dark matter and dark energy. Those essentially are material that we cannot directly observe, okay, but we infer indirectly. Okay, so closest to we have our sun. Our sun is just effectively a big ball of plasma. Okay, it's made up of hydrogen. It's a nuclear reactor, and it's ionized. You have hydrogen, and then you also have some helium as well. And this enormous object is a large structure of high pressure, and if you contrast that high pressure with the very low pressure, almost vacuum pressure of space, essentially what you have is a pressure gradient, okay? And that's how the wind blows, from a region of high pressure to low pressure, except that this is not the wind that we know, this is the solar wind. So you're having the solar atmosphere that's being stripped away from this very large pressure gradient. And you have this continuous stream of particles known as the solar wind, and this pervades the entire solar system. So every planet out there, every comet, every moon is being subjected to the solar wind. How they interact with the solar wind depends on a number of factors, whether they have magnetic fields or have electrically conductive ionospheres and so on. Or some don't interact with it at all, like the moon. Now, because because the solar wind's electrically charged, and it interacts with the magnetic field, what it does is that it drags along with it the sun's magnetic field, okay? So unlike the Earth's magnetic field, which is localized to the near-Earth environment, the sun's magnetic field is stretched all the way to the heliopause, to the outer solar system, okay? And then even though it's 1 particle per cubic centimeter, I mean, it's an extremely tenuous environment, it's still a wind in the sense that it behaves as a fluid. Okay, so what do I mean by a fluid? If you think about, say, water molecules, let's say a river or air, these particles, they don't act independently, they act cooperatively. And the reason they're able to act cooperatively is because they collide with one another. Okay, so they keep bombarding one another and they exchange information. So whatever goes on there, collisions will transport that information all across the room, and that's what makes the entire air in the room behave as a fluid, as a continuum. Now, in the solar wind, you don't get any collisions. Actually, the mean free path of collisions, that is the average distance a solar wind particle needs to travel before it collides, is 1 AU. Okay, so it's a yes. So it will come out of the sun, and only when it gets to the Earth, it will then collide to another particle. So collisions are inefficient when it comes to giving it the collective behavior. So what essentially steps in? That would be the magnetic fields. Okay, so through the magnetic fields, or generally the electromagnetic fields, you get this long-range communication between particles, okay? Otherwise, if they weren't there, then they would be no different to just, spray of particle every now and again. They don't really talk to each other. They just act independently. So it is the fact that they're ionized and they interact with electromagnetic fields, they behave as this fluid, and that's why we call it the solar wind. Now, when the solar wind impinges on the Earth's magnetic field, the Earth's magnetosphere, that's the region, the volume of space around the Earth that's carved out by its magnetic field, that acts as a shield. And so the solar wind deflects around. And the solar wind is supersonic. And so the first boundary that it will meet is a bow shock, which is a shock wave. And that is about maybe 20 Earth radii upstream. And then just downstream of that, you get the magnetopause being the last magnetic field line that is connected to the Earth. Okay, so that would be the boundary. And everything will deflect around the Earth. However, every now and again, when the solar magnetic field, also known as the interplanetary magnetic field, if it's at a favorable orientation, which is southward, it can reconnect with the northward Earth magnetic field and then open up a cavity, and some of the solar wind can access the magnetosphere. Okay, so there's a lot of kinetic energy associated with this interaction. And sometimes when it's enhanced, like when you have a coronal mass ejection, you get very large influx of kinetic energy, and that can cause the magnetospheric particles of the Earth. So there's a lot of plasma contained in the Earth's magnetosphere. Can cause them to sort of jiggle and energize, and then they travel along the magnetic field line. And just given the geometry of the magnetic field, they funnel into the polar regions, and they give us the auroras as we know it. Okay. Now, I talked about Jupiter's auroras here, and it's fundamentally different process, which I'll talk to you about. Okay, now this process will rinse and repeat. When the field lines connect, they will convect to the night side and they will reconnect in the night side because magnetic flux has to be conserved. You can't create or destroy magnetic fields. And this is known as the Dungy cycle. So most planets have magnetic fields. Well, at least for the magnetized planets, you can see they have auroras as we know it. And the top row shows auroral images that are captured by Earth-based telescopes, and the bottom row shows for the same planet auroras captured by spacecraft. So here we have Jupiter, and this is taken by the ALMA space telescope. Sorry, the ALMA telescope. And over here, this was taken by Juno when it flew past Jupiter's south pole. This is in the infrared. And at Saturn, this is taken by the Hubble Space Telescope. And in the bottom panel, this was taken by the Cassini spacecraft. This was the UV imager in the Cassini spacecraft. And over here, this is an auroral footprint that's connected to Enceladus, one of Saturn's moons. And then here you have Uranus. You can see it very, very patchy. And indeed, this is also true when you look at Voyager 2, which was the only spacecraft to fly past Uranus. You can see that there's aurora in the equator, and that's just because the magnetic field of Uranus is really, really, really unusual. Okay, it's highly tilted, and there's a very large. I mean, the planet itself is on its side, and then the angle between the dipole axis and the rotation axis is about 90 degrees. And then there's also a very large offset as well. So the center of the dipole is not at the center of the planet. And so it leads to this crazy configuration. So these are magnetized planets and they have auroras, but unmagnetized planets also have auroras. Okay, so let's say Mars, which actually has crustal magnetic fields that are highly localized. But the auroral energy is spread out across the entire planet because there's no magnetic field. So you get a very faint, diffuse aurora all around. Magnetic fields, what they do is they act as a lens. They take in this kinetic energy and they focus it onto the poles. So you get much stronger auroras. So to give you a sense of scale about these planets and their magnetic fields, here we have Mercury, and quite exciting, the Europeans and Japanese are sending twin spacecraft to Mercury, which at the end of this year, they'll go into orbit, and that mission is known as Bepi-Colombo, and that will investigate the magnetosphere. That's at least one of the science objectives, will investigate the magnetosphere of Mercury. A Mercury magnetic field is generated by induction. It's a very, very small magnetosphere that actually during coronal mass ejections, it's been shown that the magnetopause hits the surface of Mercury. And then this entire structure here fits into Earth. And Earth, of course, has its own magnetosphere. And that extends again to about 15 times Earth's radius. And then this entire structure fits within Saturn. And then you guessed it, this entire structure fits to the sort of very close neighborhood of Jupiter. So Jupiter is the largest structure in the sky. If it were visible to the naked eye, it would be the largest structure. Okay, so here are some properties of Jupiter's magnetic field. It's the strongest. At the pole, it's about 2 millitesla. If that means nothing to you, it's 23 times stronger than the Earth's magnetic field. What's quite interesting is, so the dayside magnetopause, so that is its magnetosphere that's facing the solar wind. I mentioned Earth is 15 times Earth's radius. This actually goes up to about 100 times Jupiter's radius. Okay, so an extremely large structure. Now, not only that, The day side, again, is confined by the pressure of the solar wind, but there's nothing confining the night side. So these magnetic fields, and this has been observed, extends all the way out to Saturn. Okay, so you can see here, greater than 4 AU, that's a lower limit. Okay, who knows how far it goes? It's rotation dominated, it's very fast rotating planet. So one day takes 10 hours at Jupiter. And then there's also a very significant source of plasma from its innermost Galilean moon, Io. Io is one of the most hostile environments in the solar system. It's very volcanically active. And that's because of the extreme tidal forces that it experiences very close to Jupiter. Despite the very small eccentricity or deviation from eccentricity, and it emits estimated about one ton per second of volcanic material in the form of sulfur dioxide that gets ionized by various processes into sulfur and oxygen ions, and then those become trapped in Jupiter's magnetic field, and that plasma pressure is what inflates the magnetic field to give it a much larger size than it would otherwise have. Okay. So here's an artist impression. Now, Jupiter's magnetic field is so large such that all of the Galilean moons, so Io, Europa, Ganymede, and Callisto, their orbits are permanently embedded within its magnetosphere. Okay, so there's no escape. Our Earth spends about 10% of its time in our magnetic field. And even when it does, nothing happens because the Earth is geologically dead. Okay, so it's kind of like waving a bar magnet at a block of wood. Nothing happens. But the Galilean moons are geologically active. And what that means is that their interiors are conductive. And given that they're conductive, they will interact with the magnetic fields. And you can see stuff happens, okay, when the magnetic field, I should say, the magnetic field is rotating with Jupiter's rotation rate. So the magnetic fields are always sweeping past the moons. The moons are moving along much slower in their orbital speed, okay? So when the magnetic field tries to sweep past, you can see they deform. And that deformation leads to the formation of so-called Alfvén waves. These are waves that travel along the magnetic field. That's how information travels in magnetic fields through Alfvén waves. And those Alfvén waves, since they travel along the field line, they end up into the poles, and they carry a lot of energy with them. And that leads to moon footprint on the planet. Okay, so if you're able to get a good image of Jupiter's aurora, you can see the moon footprint, and I'll show you an image later on, and you can tell a lot about what's going on with the moon, where they are, get a sense of whether they're geologically active. Actually, if you see a moon footprint, you can infer that the moon is geologically active, because again, if they weren't, nothing would happen when the magnetic field sweeps past them, and you wouldn't get an Alfvén wave launching from there. Now, what's particularly interesting as well is, Io has a dynamic interior. Again, it's volcanically active. Europa is understood to have an ocean beneath its surface. That ocean is salty, and salt water is conductive. And Callisto as well is believed to have an ocean as well. And they also have ionospheres. Okay, so they're large enough to have an atmosphere that is ionized, and that can also interact with the magnetic field. Ganymede's interesting because it's the well, first of all, it's the largest moon in the solar system, and it's larger than the planet Mercury. But it also has its own internal dynamo, so it generates its own magnetic field. So if you land on Ganymede and you carry a compass, you can actually find your way around. So you kind of have this mini magnetosphere interacting with a larger magnetosphere, and Ganymede indeed has polar auroras as well. That was seen by Juno. Okay, so how are the auroras at Jupiter generated? So there is some control from the solar wind, but not much. You're way too far out. The solar wind energy declines. I mean, the plasma becomes much more tenuous. The speed is more or less constant, but the density really falls, and your kinetic energy is density times your speed squared, or I should say your kinetic energy per unit volume. So there's very little of that left when you get far out to Jupiter, yet it somehow maintains very, very powerful aurora. The way it's able to do that, again, it's thanks to Io. Okay, so Io is the beating heart of the Jupiter system. Given that it releases all of this plasma, you can see this donut-shaped structure here is known as the Io torus. That's the plasma coming out of Io that's entrained in Jupiter's magnetic field. Over time, that plasma will diffuse radially outward. And when it does that, it's conserving angular momentum. And so that means that the increase in radial distance comes at a cost of azimuthal speed. So it will start to slow down, okay? And once it slows down, because it's a plasma, it holds on to the magnetic field. This is a top-down view of Jupiter's magnetic field. You can see that you have radially, you have the magnetic field geometry that's radially outward, but once you go too far out, you get this bend back. That's because the plasma is slowing down. So this bend back of the magnetic field, this spiral pattern, from Maxwell's equation, it tells you that if you have a curl of magnetic field, that is, if you have a sort of a circulation of magnetic field, a rotation, if you like, that must come with a current, okay, an electric current. So electric currents are formed to balance this or to sort of limit this bend back of the field. One way you can think about it is that if these currents don't form, the bend back of the field will continue on forever and it will just wind round and round and round and round. Who knows what will happen? No one knows because it just doesn't happen. So the electric current imparts a force to try and limit this bend back. Now, we all know that if you're turning on a circuit, the circuit must be closed. So if you have a current flowing, there must be a closed circuit. And the easiest path for a current to flow is along a magnetic field. There's no resistance, okay? So you can guess where the current will end up. It will end up in the poles because it will follow the magnetic field, okay? So that's how it essentially gets closed. The current is essentially the flow of charged particles. So that's essentially charged particles that are crashing into the atmosphere, generating the auroras. So here is an image, a UV image taken by the Hubble Space Telescope of Jupiter's aurora. And you can imagine, so this is the North Pole. You have the classic auroral oval, kind of as you do at Earth. But then few differences. One, as I mentioned, you have the footprint of the moons. You have Io, you have Europa, you have Ganymede. Callisto is very hard to detect because Callisto's footprint was embedded within the main emission, but actually it was discovered about a year or two ago by Juno when the main emission contracted and then the Callisto footprint became visible. And you can see that these footprints actually have a tail associated with them. That's because those Alfvén waves, when they get to the pole, they bounce back to the southern pole and they go back and forth, back and forth, back and forth, and they lose energy sort of incrementally over time. And that gives you a sort of tail, fainting tail that goes around. And I wish I put an infrared image here, but it's actually quite interesting because the Io tail was shown to actually go all the way around. So it's a very, very, very powerful interaction. And then another difference between Jupiter and Earth is that poleward of the main emission is called the polar cap. And you can see that there's a lot of auroral emission there. If you look at the Earth's aurora, it's called a black aurora. There's nothing happening poleward of the ring. Yes, I think I saw a hand up. So the atmosphere is electrically charged. The atmosphere here is the ionosphere, which is the upper atmosphere that is electrically charged. So that is, and because of that, it can interact with the magnetic field. But the aurora is as a result of the particles losing energy and emitting some wavelength. In Jupiter, it's in the UV mostly.
because I believe I had heard the auroras, and it sounded like kind of an electrical current, or like when someone touches an outlet and there's kind of like a spark or something. It sounded a little bit like that.
Yeah. So that is most likely, that is most likely associated with the ionospheric particles moving. Okay, so there are lots of currents there, and that can cause interference as well. Okay. Now, what's quite interesting is that, so one reason why we care about the auroras is because, so you can look at this image and you can imagine if I go back, this image maps to hundreds and thousands of miles away. Okay, so each time you go poleward, you're mapping to a more and more distant region outward. Okay, so that's why, for example, you see the Io footprint is most equatorward, and then when you go more poleward, you connect to Ganymede, more poleward, you connect to Europa and Callisto, and so on and so forth. Okay, so by looking at the aurora, you can get a sense of what's going on around Jupiter's environment. Yes.
The majority of plasma material that is interacting with the majority of plasma material, if not all of it, that's interacting with Jupiter's magnetic field and creating the aurora is coming from only Io. Is that correct?
Mostly Io, not entirely.
Okay.
Yes.
So these marking points that we see for the other moons is that moon's interaction with actually the material that has been released from Io that identifies them, not anything to do with anything coming from those moons.
Great question. Now, the plasma interaction, that's what gives you the main emission, okay? And actually the main emission, although it seems to be very narrow in angle, if you map it out to the magnetosphere, it's an extremely large region. That's the region where you see the bend back, okay? The moons, that's just a direct interaction between the magnetic field and the conductive moon that leads to a deformation. And that deformation launches an alphane wave that goes all the way. So these are local interactions that we see. And then what you're seeing in the main emission as you go farther out, it's a very vast region of this bend back magnetic field. That's actually beyond the orbit of Callisto. Okay. And yes, it starts life at Io.
And the other question I had was, since the aurora on Jupiter is basically fueled by Io, it's perpetual. I mean, Jupiter will always have this aurora, unlike here where they come and go.
Yes.
It's there all the time.
Yes, you always have the aurora. There is a lot of variability as well. To some extent, the solar wind, but not a lot. And also, some speculate that it's tied to Io's volcanic activity. It's very difficult to prove because there's a finite time between a volcano and for this multi-step process to take place, and by the time it gets up to Jupiter's pole as an auroral emission. I mean, it can take weeks for the plasma to diffuse out. So yes, there is significant variability. Presumably that variability is tied to magnetospheric activity, and then presumably that magnetospheric activity is tied all the way back to what's going on at Io, and some variability in the volcanic activity, yes. But it's speculative at this point. Okay. All right, then another reason, so Jupiter's auroras are very, very, very powerful, and that actually it affects the climate at Jupiter, which is not the case at Earth. There's this so-called energy crisis at the outer planets, where their upper atmospheres are actually measured to be so much hotter than what we would expect from solar radiation alone. Okay, so for example, here's an image. This is data collected by the Galileo spacecraft when it dropped a probe into Jupiter's equatorial atmosphere. And over here, you have temperature on this axis. And this axis is the altitude. And you can see that when it got to the ionosphere, the temperatures were much higher than what was predicted based on what they thought it would be based on just simply intercepting sunlight. Okay, so Jupiter, it's 4.5 times hotter, and you can see it Saturn, Uranus, Neptune. It's some factor of something hotter, and the reason is the aurora. So here's a top-down view of Jupiter's north pole, and here we're looking at temperature, and you can see where the aurora is located. It's a very sort of hot spot, the largest temperature, and then there's a smooth gradient as you go equatorward. So the aurora dumps a lot of energy and heat into the polar region, and then that gets transported meridionally into the lower latitudes. Okay, so lots of climate implications as opposed to that, which is important when we're trying to understand compositions and habitability and so on and so forth. Especially now we're in the age of exoplanets. There's a lot that we can learn from our solar system's planets and make, some educated guesses about what's going on in planets that we'll never reach, or at least send a spacecraft to. Now, one thing I should say is that so what is quite interesting is that Io, based on the auroral observations, not in the UV, but from radio. So in the 1950s, radio emissions were detected from Jupiter. That's because it has a magnetic field. Magnetic field charged particles can lead to radio wave being emitted, which can be observed at Earth. And from that, by measuring the periodicity of these radio signals, they were able to infer, A, that Jupiter has a magnetic field, and B, what the rotation rate of Jupiter is, and then finding a component of that radio signal that is in sync with Io's orbital period. Through that, they were able to infer that Io is geologically active. Okay, now there's no way you can do that with a telescope, and actually, there's you have to send a spacecraft to a body to determine that it's geologically active, and they were able to infer that from radio signals. So this is a really, really sort of hot topic when it comes to exoplanets, sort of what to look for. There are ways you can tell that it has a magnetic field, if you can detect radio signals, and if you can detect radio signals that far exceed its rotation rate, then it's probably an exomoon that is geologically active, much like Io. Okay, so here's the Juno spacecraft. So it's powered by solar panels, has very large solar panels, and actually we're approaching the 10-year anniversary of Juno, which will be on July 4th. And it has a number of instruments, about 10, both remote sensing, so in the UV, that's the UVS instrument, and then GIRAM is the infrared, and JunoCam is the visible. This is an outreach camera, but actually it's done a lot of fantastic science. And then it also has a number of in situ instruments that measures magnetic field. You have a magnetometer, and also low energy particles, high energy particles, that's plasma, and as well as waves. Waves here are essentially fluctuations in the electric and magnetic field. And of course, there's also another remote sensing instrument, which is the microwave. So as I mentioned, Juno gave us unique access to Jupiter's polar regions. So as it flies over the pole, it cuts through the magnetic fields and it measures the local charged particles that are streaming into the aurora. And it also measures the electromagnetic fluctuations. Those are what accelerate the particles there. So we get all these fantastic measurements that gives us a better understanding of this extreme environment. And in addition to that, because of the inhomogeneity in Jupiter's gravitational field, we get an orbital precession for free, okay, so without spending fuel. So Juno comes up from the North Pole. So PJ01 is the first perijove, that's the first orbit, and perijove being the closest point to Jupiter. So you can see that it zooms from the northern pole to the southern pole in about 2 hours. And then it comes back around to the second perijove. And over time, that orbit evolves such that the line of apsides migrates in this sense. And so what that means was that we were at a point, very exciting time in 2021 in the extended mission, where the orbit evolved substantially enough such that the radial distance, well, the distance at which across the equator got closer and closer and gave us opportunities to fly past Ganymede, and then later Europa, and then Io. We got 2 Io flybys, and I'll show some images here. And now we're actually beyond this stage, and we're sampling the Gossamer rings. And also looking for some of the inner moons, which we know very little about, so like Adrastea and Amalthea and Thebe and so on. In addition to that, as someone who's interested in auroral physics, you can see that we have very large altitudinal coverage over the North Pole. So we get the full extent of the auroral acceleration region here, and we've come up with lots of fantastic and fascinating science. Yeah, so actually, this was a fairly recent discovery, and I'll talk a little about it here. You can see there's density depletion. I'll talk about this in a moment. So I'll just introduce this. These are just 3 different auroral regions, the diffuse aurora, zone 1, zone 2. Zone 1 carries the upward current. Zone 2 carries a downward current because you must have a closed loop. These are all the various fields and particles phenomena that were discovered. And since then, we've been working to tie all of these together. You know, how do these waves interact with these particles? What's the underlying plasma physics that's causing the energization and the acceleration? And then how do the energetics in this region here, in the invisible region, account for the brightness, so the stuff that we see? Now, one of the big discoveries that was found was that where the aurora is, so here, this is just an auroral image of Jupiter. We're looking down, and this is just a cut that we've made here. So Juno flies past here. That's a diffuse aurora, and then that's zone 1, and then the red part is zone 2. The ionosphere is significantly depleted. So I mentioned that the solar wind is 1 particle per cubic centimeter. So this is 10 to the minus 4 particles per cubic centimeter. Okay, so four orders of magnitude lower. So it is an extremely depleted environment. Why? This auroral energy is, you have so much energy being dumped into the atmosphere. These particles, they get energized and they exceed escape speed. Okay, so they overcome Jupiter's gravitational field, and so you have that sort of excavation in that region. But you have something else happening, which is you have a very depleted region in plasma, but you're also very close to Jupiter, so it's very highly magnetized. So the magnetic field is extremely, extremely high, and the ratio of the magnetic field to plasma, which is an important plasma parameter, so called the plasma beta. So that ratio, maybe we'll do the inverse so it can be a big number, is extremely high. It's the highest we've measured anywhere in the solar system, whether it's near Earth, near Saturn, or near the Sun. And what we found, this is just in the last year or two, and this is an active area of research at the University of Minnesota. I'm collaborating with, perhaps you've heard of Professor Bob Lysak, who I understand has given a talk here before, or so he told me. So this regime, this plasma regime at Jupiter actually shares more commonalities with stellar regimes than it does with other planets. Jupiter is actually more like stars and sort of pulsars than it is like even Saturn as well. Okay, so the plasma physics is very, very extreme. And I could go on about this, but I'll move on to something else for now, and I'm happy to talk more about it later if anyone has any questions. So another thing that Juno was able to constrain was the interior of Jupiter, and that's again by virtue of these polar orbits. You can get sort of latitudinal slices of its interior, and the way it does that is actually with no special instrument. It does that basically by looking at the signal, analyzing the signal from Jupiter, the radio waves that are coming from Juno, not Jupiter, Juno. So Juno's talking to us at Earth, and it's sending these signals. And we know the frequency of these signals because that's how it's specified. We designed it to talk to us at a certain frequency so we can know who's talking to us. But then we see that frequency sometimes being stretched and sometimes being squished. Okay, that's Doppler shift, right? So sometimes it's red shifted and sometimes it's blue shifted. And that's because Jupiter's interior it's not perfectly uniform. It's highly non-uniform. And there's some regions that are denser than others. Now, if it's passing over a certain region that it's quite dense, what's going to happen is it's going to pull on Juno a little bit more. So Juno will recede away from us, and the radio signal will be redshifted. Okay, and then if you go over a region where the density is a little bit low, then the reverse happens. The signal will be blue shifted. Okay, so you can compare what the computed orbit is, nice analytical orbit, against what the actual orbit is, where it's wobbling back and forth. Okay, and you can use that information to constrain the interior of Jupiter. So really, this is stuff done by not me, but by some very clever people at JPL. Okay. Now, another way of looking at Jupiter's interior is looking at the microwave. So the microwave has 6 different channels with six different frequencies. So they have 6 different sort of penetrating depths. And here's a very nice image of the great red spot. So here's the image from the visible camera. But then you can see, like layers of an onion, you get each channel of the microwave gives you the depth. And then you can pretty much see how far it goes, which is down to here. So this was another exciting result from Juno. As you can imagine, a very fast rotating planet. You get lots of cells. So for example, Earth, you're probably familiar with the Hadley cells, which are these equatorial cells that go up to the tropics. But each hemisphere will have 3 cells. At Jupiter, you have many, many more. And they're also quite deep. So it's truly a hostile planet. Okay, so this was the image that was taken of Ganymede. So that was the first moon flyby in June 2021. It was an extremely exciting time. It was maybe about 2 years of planning, what sort of measurements we could take, and exploring the trade space. People like me who work with in situ instruments, fields and particles, we want to get as close as possible, but those who take images want to be as far as possible, so you can take sort of a global view. So it was a very, very exciting time working with different scientists and see how we can get the best out of the flybys. And again, as a reminder, what we're not seeing here is Ganymede's magnetic field. Juno flew through the magnetosphere of Ganymede, and so it was completely removed from Jupiter's magnetic field because these two don't mix. And then the UV image found very faint polar aurora on Ganymede. Now, Ganymede has a very tenuous atmosphere, so the way its aurora is generated and the way it's sustained is that you have the particles, they stream along the field line and they precipitate, they crash onto the surface of Ganymede. And that leads to sputtering of particles that give you sort of a temporary atmosphere that the next train of particles come and crash into the atmosphere and cause it to glow. Then you have Europa, which is a future target for NASA's Europa mission. And Europa has a salty ocean. It's not very well constrained. The depth is not well known, and the salinity is not well known. So that's going to be one of the objectives of the Europa Clipper mission. And you can see that it has a seemingly young surface, and that's an indication that it is geologically active. Because the older a body is, the more craters you would expect to see. However, if it's supposed to be old, but it doesn't look old, then there's something that is rejuvenating the planet, and that is coming from the interior. And of course, Europa is a very exciting target, Ganymede as well. With the oceans, they've just ushered in a new era of, looking for signs of life. Now, before these moons were known to be interesting, so that was before the 90s, it was thought that if you wanted to look for life, you look at the so-called Goldilocks zone in any solar or stellar system. You don't want to be too close because then water will be in its gaseous state, and you don't want to be too far, otherwise water will be in its icy state. So you want to be somewhere where Earth is, or Mars, where water will be in its liquid state on the surface. Now, we are way beyond the Goldilocks zone here, yet we do have water, because it turns out you can have water beneath the surface, and that water is being kept liquid, especially if you're orbiting a very large planet. The tidal forces, the friction from the tidal forces will keep the heat going, and there's also some antifreeze as well to lower the melting point. I should say one thing about Ganymede is that Ganymede contains more water than all of the Earth's oceans combined as well. And then you have Io, no water. You're a bit too close to Jupiter, and the tidal forces are very aggressive. And you can see it's a very tortured world. You can see all the volcanoes. And I was very lucky the second flyby, we were able to capture a double volcano coming out of Io here. So really, this is the source of, all of the dynamics of Jupiter's magnetosphere and the resulting auroras. Yes, yes, most of the particles coming from the magnetospheric particles, but not the atmospheric particles of Jupiter. Yeah, and then this is looking at Io through infrared. So what wasn't visible in the previous picture, now you can see these are all volcanoes and lava lakes. So a truly hostile world. Okay, so as I mentioned, why are we interested about about these moons? So again, the question of habitability. I think maybe this is one question that piques our interest as humans. Is there life out there? Where should we go to look for life? And the thing to do is, finding life is extremely difficult. It's maybe not possible even at this, with current technology. But what we can do is we can look for the conditions that are needed to sustain life. And there are 4 ingredients. You need liquid water, you need hydrocarbons, you need a source of energy, and you need stability over time. You don't want the environment to change too much, because if there were life, or if life were to form, then you need some stability for evolution to do its thing. So all of these, well, at least these 3, stability is a bit subjective. If it's life as we know it, then we can make some predictions about how long you need for evolution to do its thing. But if you're in a very different environment and the genetic makeup is very different to ours, then that's a big unknown. But there's liquid ocean. We know it's there, and I'll talk a little bit more about how we know it's there. The hydrocarbons, again, they've been measured with spectroscopy, and there's a source of energy. Well, we know if the ocean's liquid in a very, very, very cold region, then there must be a source of energy, and we know that source of energy is tidal forcing, but also from radioactive material as well. Okay, so how do we know that there are subsurface oceans on these moons? This was discovered by the Galileo spacecraft, the first orbiter around Jupiter. And this was actually done using magnetic field observations. So as I mentioned earlier, if you have a magnetic field that's sweeping past the moon, okay, yep, I'll be done soon. If you have a magnetic field that's sweeping past the moon, that magnetic field will deform, suggesting that the interior is conductive. And how much that magnetic field deforms depends on how conductive the interior is, okay? So you can constrain that conductivity based on the measured deformation. So what I'm showing here is you're measuring a magnetic field, and that's the vector sum of different contributions. You have Jupiter's magnetic field, and you have other contributions, but most importantly, there's one contribution due to the ocean. So you can separate all of these out, and you can be left with a magnetic field from the ocean. You can use that signal to infer what that conductivity is. And if you look up the encyclopedia conductivity of 1 Siemens per meter, you'll find it's salt water. Okay. So what I will do is maybe I will just highlight Enceladus because I'm being told that I'm over time. So Enceladus is at Saturn, and it's quite an interesting moon because it's only 500 kilometers in diameter. And when Cassini got there, it was thought, there's nothing to see here. But actually what they found was indeed from magnetic field observations, when Cassini flew past Enceladus, the magnetic field seemed to deflect around it. And the magnetic field seemed to deflect. That shape from that deflection suggested that the obstacle was much bigger than Enceladus, which was surprising because it's so small, it cannot support an atmosphere. So the only possibility was there's something that's continuously coming out of it. Okay. And indeed, a plume was discovered from Enceladus's south pole. Okay. So when the cameras turned around, they found this jet. How do you know there are hydrocarbons? Cassini turned around and flew right through that plume and measured lots of hydrocarbons there. Okay. So some exciting, these are my last 2 slides. JUICE, Jupiter Icy Moons Explorer, is on its way to Jupiter. It will arrive in 2031. It's a European mission. And then it will go into orbit around Ganymede in 2032. And that way would be able to fully understand, since Ganymede has its own magnetic field, to separate out its own magnetic field from Jupiter's magnetic field, you need an orbiter. So it'll be the first time a spacecraft orbits a moon other than ours. Europa Clipper is a NASA mission on the way to Europa, an ocean world, again, to explore and investigate habitability and focus on the liquid water and the chemistry and energy. And the hope is that far into the future, we have the first Uranus orbiter. Again, we only know a little bit about Uranus from the Voyager 2 flyby. And again, here's the geometry of Jupiter's magnetic field that I was trying to explain. You can see that A, it's on its side, okay? So that's the rotation axis. B, you can see the tilt between the rotation axis and the dipole axis. And then you can see the offset. It's not at the center. So it's just extremely difficult to think about how charged particles move. And that's why you get this patchy aurora all over the place. In terms of the timing, I'll say if everything goes to plan, so I've been at the University of Minnesota now, it's my 4th year as an assistant professor, and I'm actively working with the community to get this off the ground. When it gets there, again, if everything goes to plan, I'll be looking at the data in my retirement. And I'll actually say that that's actually one of the beauty of working in planetary science or astroplanetary sciences. Everything happens on a decadal timescale. So I did my PhD on Cassini. I joined in 2012. Cassini had been there for a few years. I had the best time. I was enjoying the fruits of other people's labor. Some of them, are not there anymore. And so there's this kind of community service sort of mindset that, now I feel like, it's a time, try to get the next mission off the ground, and that's for the next generation to enjoy the data. All right, well, thank you, and sorry for going over time.
That's all right. So thank you, Dr. Sulaiman. So if people have questions, please go up to him later. Let's wrap up. We have to get out of the room here pretty soon here. So again, thank you for coming, and hopefully we'll see you again here. All right, then lastly, if you want, and you can join us too, we usually have a get together after the meeting here at the pizza place. So at Pizza Luce. So next month, July 2nd, 7 p.m., we're going to have various MAS speakers, and hope to see you all here. So have a good June. Thanks.